Great morning, everyone. Welcome back. Let's look today at another type of series, in particular alternating series, and test them for convergence or divergence. Quite simply, an alternating series is a series whose terms alternate between positive and negative. I've got two examples up on the board here right now. The first example, notice that all that's happening is it's taking this sign, and the sign is still appearing, sine 1, sine 2, sine 3. But this negative 1 to the n minus 1 here is causing every second term to be negative and every other term to be positive. Down here I've got 2 over n squared plus 1. I'm plugging in n equals 1, n equals 2, n equals 3. But again, the terms are alternating between negative and positive. That's because when the power of negative 1 is even, it's going to be squaring or taking the fourth power of a negative number. It's going to end up being a positive term. So like if I put negative 1 in, or n equals 1, and I get 1 minus 1 is 0, negative 1 to the 0 is positive 1, and that's why the first term is positive. N equals 2, I get negative 1 to the 2 minus 1, which is 1, and that negative 1 to the 1 is negative, and that's why the second term is negative. And of course, every second term will alternate between positive and negative, even and odd, and you get this alternating series thing going on. Typically write the series with our choice of alternator, so to speak, and you choose which one you want based on whether you want the first term to be positive, in which case you use this one, or you want the first term to be negative, in which case you use this one. And we call Bn this part that we're actually plugging n into. It's kind of like if the alternation weren't there, that would be the term of the sequence. So we're just going to call that Bn. Turns out, evaluating these for convergence or divergence is not going to be difficult. It's going to be quite straightforward. You've got two relatively simple conditions to check that will guarantee convergence. So let's look at them. The alternating series test. I have in my pocket an alternating series. Okay, so I'm calling the piece Bn and I'm alternating by a negative 1. I'm going to choose to write it with the first term positive, so I'm using the negative 1 to the n minus 1. That's just out of aesthetics, really. It doesn't matter. This works even if you have n plus 1 and n plus 3, doesn't matter, because really all of these convergence and divergence things are about infinity. It doesn't really matter what's happening at the very beginning. So if it's non-increasing, the terms that you're alternating are non-increasing, meaning they can't go up. They're getting smaller or they're staying the same size. This is very similar to the integral test where the function had to be decreasing, except this is a little looser. They cannot increase. So if they stay the same, that's fine. We don't care, but we just want to make sure that the sequence terms that we're adding up to form our series are not going up. Usually this will involve, of course, a derivative, just like the integral test did. The second condition is that the limit of those bn's needs to be 0. So not only do the terms have to be non-increasing, they also have to go to 0. Basically, this is because if this were going to go to like 3, then you'd get 3, negative 3, 3, negative 3, 3, negative 3, and then you don't have a convergent series. You have something that just alternates between negative 3 and 3. It has to go to 0, and it has to go to 0 in a non-increasing way. It can't go down, have a little hump, and then go back down. It needs to go down the whole time. So let's look at a couple of examples of this, and we'll see that this isn't going to be terrible. The most work that you're going to have to do here is in part 1 to use a derivative to find the intervals of increasing, decreasing, and making sure that it's decreasing or the same on 1 to infinity, the things you're adding over. So let's look first. Oh, then the series is convergent. Let's look first at the alternating harmonic series. the alternating harmonic series. So you got 1 over n, and you alternate it. I claim, and I'm going to show you in a second, that this is a convergent series. And I say here, even though the non-alternating harmonic series, 1 over n, is a divergent series. In fact, it's the first example of a divergent series whose terms go to 0. And it is our it's in our toolbox of comparison test series. The harmonic series, a p series with p equals 1, is kind of our favorite divergent series, really. So let's show that the alternating harmonic series converges. And the alternating part is really the important part. So number 1, I'm just going to say Bn is 1 over n. Just to write it down. It's kind of clear that that's the case here, that the alternating part is -1 to the n minus 1, and then the Bn part is 1 over n. So when we check the conditions for the alternating series test, they're going to be about 1 over n. Is this non-increasing? Well, in other words, is Bn plus 1 less than or equal to Bn? Well, Bn plus 1 is 1 over n plus 1, and Bn is 1 over n, and is this true? Yes, because a bigger denominator gives you a smaller fraction. And n plus 1 is bigger than n. It's strictly bigger, but I'll put the greater than or equal to sign there, just to play with the conditions here. So yes, this is a non-increasing, in fact it's a strictly decreasing terms in the series. And then number 2, the limit of these terms, that's the limit of 1 over n, is 0. So check. So by the alternating series test, AST, this series converges. And that's all there is to it, really. Are the terms non-increasing? And do the terms go to 0? If yes, you've got yourself a convergent series on your hands. All right, let's look at another example. Let's do 1 over ln 3 minus 1 over ln 4 plus 1 over ln 5 minus 1 over ln 6, etc. Write this as a series. It's going to have a -1 there. And because it starts with a positive term, I'm going to start this with a -1 to the n minus 1. And the Bn part is going to be 1 over ln something. It's not going to, it doesn't start at ln 1 and ln 2 and ln 3. It starts at ln 3 and ln 4 and ln 5. So it actually starts 2 more. So I plug 1 in, I get ln 3. I plug 2 in, I get ln 4. So my Bn is 1 over ln of n plus 2. So 2 questions. 1, is this decreasing or non-increasing? And 2, do these terms go to 0? So first things first, non-increasing. Well, Bn plus 1 is less than or equal to Bn, i.e. is ln of n plus 3 less than or equal to, 1 over ln of n plus 1 less than or equal to 1 over ln of n plus 2. And that's yes, since ln of n plus 3 is bigger than or equal to ln of n plus 2, because ln is an increasing function. So it's an increasing function, so ln of n plus 3 is bigger than ln of n plus 2, which means the fraction 1 over ln of n plus 3 is less than or equal to the fraction 1 over ln of n plus 2. Excellent. And do the terms go to 0? Well, that's the limit as n goes to infinity of 1 over ln of n plus 2, which is 0, since lns go to infinity as n goes to infinity. So the series converges by the alternating series test. So I've just checked. I said, hey, look, it's non-increasing. In fact, it's a strictly decreasing function again. And the terms go to 0, so it converges. I'll take a pause right now to say, look, if you have a function that increases, you can't use the alternating series test. If you have a series whose terms don't go to 0, you can't use the alternating series test. So the alternating series test is nice while you can use it. If you can't use it, you can't use it. You got to use something else, a comparison test, or perhaps some sort of divergence test, etc. All right, let's do one more example to finish this up. Let's look at series -1 to the n plus 1, n e to the negative n. And let's test this for convergence or divergence. We can clearly see this is an alternating series, but now we need to check, in order to use the alternating series test, whether 1, the terms are non-increasing, and 2, whether the terms go to 0. So let's look at number 1. Is it non-increasing? And in this case, we've got Bn equals n to the e to the negative e to the negative n, which is n over e to the n. And now we've got an example of where it's not 100% clear that this is a decreasing, or I should say non-increasing terms. So we need to use derivatives in order to tell if this is decreasing on an interval or non-increasing. So what we do is we consider the related function f of x equals x over e to the x. This is the function which passes through every point of the terms of this series as we need. And if this is a decreasing function, it means the series terms are also decreasing. So we calculate the derivative using the quotient rule. So the derivative of x is 1 e to the x minus e to the x times x all over e to the x squared. So I'll factor out that e to the x I see there. I'll just write this as e to the 2x. So there's our derivative of that thing. And then we're going to see, where is this increasing, where is this decreasing. So first we'll see where it could change, where the derivative is 0, where we have critical points. So we'll solve for the critical points. The derivative is 0 when, since this is a fraction, when the numerator is 0. And the numerator is 0 when e to the x is 0, or 1 minus x is 0. That can't happen. E to the x is never 0, so it's 0 when x is equal to 1. Now, at x equals 2, so I'll choose a number bigger than 1. I know that the critical point is at 1, so now I need to choose something between 1 and infinity to see whether the function is decreasing or increasing on that interval. And I'm choosing x equals 2. F prime of 2 is equal to e squared times 1 minus 2 over e to the 4, which is equal to negative e squared over e to the 4, which is less than 0. So I've discovered that the critical point is at 0, and at x equals 2, this function has a negative derivative. So it's decreasing on the interval 1 infinity. Excellent. And so it's non-decreasing or non-increasing. On 1 infinity inclusive, because it was 0 at 1, so it's flat, and then it starts decreasing for the rest of the interval. So Bn's are non-increasing. On 1 infinity. So using the derivative, I've shown that the terms either decrease or don't change on the interval 1 to infinity over which I'm adding it up. And that's what it means to be non-increasing. So that's condition 1 checked. Condition 2, the limit as n goes to infinity of bn is equal to the limit as n goes to infinity of n over e to the n. So the first part we had to remember our derivatives. The second part we now have to remember how to take limits. And we notice that the limit of the top, the limit of n here, is infinity. The limit of the bottom is infinity. So this is an infinity over infinity form. And we're going to use L'Hopital's rule. So we use L'Hopital's rule. The derivative of that is 1. The derivative of that is e to the n. And this is 0. Because 1 over e to the n gets infinitely large. 1 stays the same. That limit is 0. So the second condition is also met. So we use the derivative to show it was decreasing on that interval. And now we showed using L'Hopital's rule that the limit of the terms is going to 0. So by the alternating series test, the series that we were testing converges.